Okay, so welcome back. So in the previous video I showed you how you can turn on a transistor and basically about the voltage over here, which I called V of C. The voltage over here that I called V of C, which is the collector voltage of the voltage that you have on the collector terminal of the transistor with respect to the ground, right? So now we are going to use this concept in this circuit over here, right? So this is supposed to be V of S, and so we are going to use this concept over here we are going to use the concept in this type of circuit. So this circuit, essentially what we have here is, let me erase these things because we don't need them anymore, so that we can write a couple of things over here. Okay, so basically what we have here is a circuit, and you can see that in this circuit we have a resistor. Let's call it R1, and let's call it R2, and let's call it R3 and R4. R3 and R4. Let's call this Q1 and let's call this Q2. And this switch has basically three terminals here. This is I'm going to call this A and B, meaning that position A and B. This is common. So now what you want to do is that basically what you want to do here is basically you want to let me read through this example. Okay, so essentially what you want to do here is that you want to find the values of these resistors R1, R2, R3, and we'll call this Q2 as well. R1, R2, R3 in such a way that you can ensure that basically when this, we talked about this in the previous video as well. Now I'm not really sure, I have to reason it out, but essentially what happens is that when this switch is in one of these positions, this transistor is on, otherwise it is off, right? So you can basically assume that in one position this transistor Q2 is on, and in the other position it is off. So you want to basically choose the values of these resistors in such a way that in one position this transistor is on, and in the other position it is off, right? That means that in one position the transistor is saturated, in the other position is not saturated. And again, what it means is that in one position the whole basically supply voltage over here is dropped across this resistor R4, and in the other direction, in the other position, there is no current flowing through this branch going to the ground, right? Now of course the value of R4 is usually given to you because this is usually your load. You usually know what sort of value you have over here. And so let's say that, for example, your R4 is equal to basically 100 ohms, and let's say that your beta 1, which is the beta related to this transistor Q1, is equal to 100, and your beta 2 is equal to 20, right? So that's your situation here. So in this kind of problem, you always need to basically start from this side of the circuit and then work your basically work your way through the circuit, go from R4 to R3, R3 to R1, and then back to R2, and then you're done, right? That's how you do this. And you essentially need to use a little bit of logic and reasoning in order to know what to do there. So now so first of all we need to know basically what is going to be the basically what's going to happen to R4 if basically this switch is in position A or B. So if the switch in position A, so that means that the base of this transistor is connected to the positive rail. And when you are connected to the positive rail, that means that there is a current going through the base emitter junction of this transistor, and so you will have basically you will have a collector current. Since you have a collector current, this transistor is turnn on, right? Since this transistor is turned on, then naturally there is no voltage here. All of the voltage is being dropped across this resistor, right? That means that there is no voltage here with respect to ground. And so what that means is that now there is no voltage on the base of this transistor, and when there is no voltage on the base, there is no current through the base, through emitter to the ground, and as a result there is no the transistor is of course turned off, right? So then that means that Q2 is, in this case, is off. And of course in the other case the Q2 is automatically going to be turned on, but we will go through that as well to show you how you can actually think about this in such a way that your line of reasoning works, basically. Because I have actually worked a lot on these circuits. I have been working a lot on these, and I know basically essentially how to think about them. That's not easy to get. It takes hours of reading and thinking, and if I can pass it on to you, that would be really beneficial if you happen to need that. So now if the switch is basically is in the position B, then basically what happens is that then the base of this transistor Q1 is tied to ground through this resistor to ground. And there is a specific reason why. I mean, you might ask, why is there a resistor through to the ground, and they essentially, this is some sort of design precaution that designers and engineers do in order to make sure that this transistor, that when it is tied to ground, it's really tied to ground, that there is no way that any current can pass through to the base of this transistor. Now I don't really know why that's important, I mean, or why that works, but essentially it's something that you usually do when you want to ground the base of a transistor. You have to use a resistor whose value is somewhere between 20 kilo ohm to something about 1 mega ohm or something like that. So some resistor you have to put between the base of the transistor and the ground, meaning that you don't ground it directly, you have to pass it through a resistor, and then the resistor goes to the ground, and for whatever reason it makes sure that the transistor never turns on. So that's basically what I know about this. Now, so when you have this type of thing over here, I mean, when when the base is tied to the ground, there is of course no base current. As a result, there is no collector current. And since there is no collector current, that means that this voltage over here, it goes directly through R3 to the base of this transistor Q2, and it turns Q2 on. And since Q2 is on, then there is collector current for Q2, and therefore you can say that Q2 is now on, right? So that's basically how you can think about this circuit in general. That's the first thing to know. And then you need to, and then we will work our way through basically all of these resistors. Okay, so now the way that you can think about this is a little bit, I mean, you need to know how to think about this, because you can very easily confuse yourself. So, or at least what I used to do. So, so essentially, basically, when you want to find the essentially when you have a circuit over here that a simple NPN transistor, there is a resistor over here that goes to the base of your transistor. The collector goes to some resistor, which is your load, this thing over here, and this goes to the positive supply rail, and this also goes to the positive supply rail, and this goes to the ground, right? And this is, for example, R of B, and this is, for example, R of C. That's basically what you would do. And then of course you choose this resistor in such a way that enough current basically flows here, so that the transistor is set to be turned on, right? We have talked about this before, so I don't have to go over this over and over again. So that means that you have to start from here and then choose each and every one of these resistors in such a way that this acts as the base resistor for the transistor Q2, right? That's basically what you would do. So essentially, if this transistor Q2 was supposed to be turned on, so of course then you would need to have enough current basically flowing here. For enough current to be flowing in here, that means that then, let me see what sort of supply voltage we have here. The supply voltage is over here is 10 volts, right? The supply voltage is 10 volts. So that means that you want, if this transistor is supposed to be turned on, you want your supply, basically the whole supply voltage, to be dropped across this resistor. So that means that I just simply basically apply the ohms law to this resistor to see what is the current in this branch. So V is equal to IR, and that basically means that I want the voltage drop across this resistor to be 10 volts, and 10 volts, and I want to know what sort of current I need for that, and the resistance value over here is 100 ohm, if I'm not mistaken. 100 ohm. So that's times 100 ohm. So that means that I is the same thing as 10 volts by 100 ohm, which is the same thing as basically 1/10 of an amp, right? So the current that I need over here is 1/10 of an amp. That means that if I call this current, if I call this I of basically C2, if I call this I of C2, I of C2 is supposed to be 1/10 of an amp. And that basically results in the fact that the whole supply voltage, which is 10 volts up here, will be dropped across this resistor, and then the transistor is turned on. Okay. So I'm going to write down these all of these over here, which means that basically then I of C2 is supposed to be equal to 0.1 amp, which is basically 100 milliamp, right? Next, what you want to do is that you need to choose this resistor in such a way that 100 milliamp can actually flow in this branch over here. And that you can do using the same equation that we said that basically I of C to I of B is equal to beta, right? But this I of C is over here is the same thing as 100 milliamp. So I'm going to write this as 0.1 amp divided by I of B is supposed to be equal to beta, and the beta of this transistor is 20. That means that 20 times I of B is the same thing as 0.1 amp. That means that I of B is the same thing as 0.1 divided by 20 amp, and that's the same thing as what is 0.1 divided by 20? Well, you know, I'm supposed to know all of these things, or at least I'm supposed to be able to do these pretty fast because I'm a mathematics teacher. It's 0.005 amps, or essentially 5 milliamp. It's the same thing as 0.005 amp, which is the same thing as 5 milliamp. So that means that the current that has to go through basically that has to go through this branch, or at least the current that is supposed to well, of course, because I cannot change the value of this R3, the value of R3 is set. You see, basically I have to make compromises here. So I want this current that goes essentially through here to be basically, I want this to be 5 milliamp. That is I of B, which is this current over here, and that we got basically based on this equation. I of C to I of B is equal to beta. I of C is the collector current that you get from here, which is 0.1 amp, 100 milliamp, and divide by I of B. Then I of B becomes basically this current that goes through here, essentially, when this transistor is not conducting. But since I have to make compromises, and this I cannot keep changing this resistor all the time, I have to basically to settle with one single resistor. I have to choose this resistor in such a way that this current becomes basically becomes 5 milliamp, right? So how can I get this current to be 5 milliamp? So that means that basically this current over here, the current that flows from this node, whether it goes this way or goes that way, doesn't really matter. But at the end of the day, the current that goes over here, well, I'm going to call this, for example, I'm going to call this, for example, I of 3. I'm going to call this I of 2, and I'm going to call this current I of 1 for the sake of simplicity, because that way you will end up with many types of notations for the current, and that would confuse you. But this is okay. I mean, this one is, there's nothing wrong with this. Now, essentially, I want this current, which is this thing over here, to be 5 milliamp, right? So that means that I of 2 is supposed to be 5 milliamp. If I of 2 is 5 milliamp, then this resistor has to be some value, like for example, you can simply apply the Ohm's law to this resistor to find out what this resistor has to be. So V is equal to IR, and the voltage across this resistor, I'm going to take it as the supply voltage, because you can see that the supply voltage comes over here through this resistor, goes to the base of the transistor, to emitter, to ground, right? Now your supply voltage is 10 volts, so you don't have to worry about the voltage drop across the base emitter junction. So that means that the whole voltage is essentially across the resistor. And so that means that then the voltage over here is 10 volts, and your current is basically 5 milliamps, 5 into 10 raised to the power negative 3 amps times R. And that means that R is the same thing as 5, actually 10 is the same thing as 10 volts divided by 5 into 10 raised to the power negative 3 amps, right? And 10 divided by 5 is equal to 2, and then that's the same thing as 2 into 10 raised to the power 3 volts per amp is ohm, right? So that's 2 kilo ohm. That is 2 kilo ohm. That means that your R3 has this resistor over here has to be 2 kilo ohm, right? Now, one thing that you need to take into consideration is that basically now that we have chosen this resistor for this branch, then the current for this branch remains essentially 5 milliamp whether we like it or not, right? That means that now, and then this transistor, sometimes it's turned off, sometimes it's turned on. When it's turned off, it's not important, of course, and you don't have to worry about that. When it's turned off, it's essentially tied to the ground, of course. When it's turned on, if it is supposed to be turned on, then basically then essentially the current over here has to be 5 milliamp. That means that now this current over here becomes the collector current of this transistor, right? And we have already found the resistor for the collector resistor. We have already found that, right? And then the only thing that now we need to do is that we need to make sure that this resistor is chosen in such a way that this current can actually flow in this branch, which means that essentially, again, I need to apply I of C to I of B is the same thing as beta. And I know that the beta of this transistor is 100, so that means that the 100 is equal to I of C, which is this current over here, I of 2, which is 5 milliamp, 5 into 10 raised to the power negative 3 amp, and divided by I of B, which is basically the current going through this branch, this I1, right? So that means that then basically I of B times 100 is the same thing as 5 into 10 raised to the power negative 3 amp, which means that I of B is the same thing as 5 into 10 raised to the power negative 3 amp divided by 100, and then this 100 goes to the numerator, becomes 10 raised to the power negative 2. This is 10 raised to the power 2, then goes to the numerator, becomes 10 raised to the power negative 2, 10 10 raised to the power negative 2, 10 raised to the power negative 3 is 10 raised to the power negative 5. That's 5 into 10 raised to the power negative 5 amps, which is like half a microamp, I suppose, right? Or 50 microamp or something like that. That's not important really. But what's important is that this I1 is supposed to be now 5 into 10 raised to the power negative 5 amp. This I1 is supposed to be 5 into 10 raised to the power negative 5 amp, right? And based on that, now you can choose this resistor. Based on that, you can choose this resistor. So how do you do that? So you want basically this, you want the current over here, you want the current over here to become 5 into 10 raised to the power negative 5 amp. And so the supply voltage over here is 10 volts. If I apply the Ohm's law to the resistor R1, I'll have basically the whole supply voltage is across this resistor, so that's 10 volt, and the current going through that is 5 into 10 raised to the power negative 5 amp times R, which means that your R is going to be equal to 10 volts by 5 into 10 raised to the power negative 5 amp, which is the same thing as this is a 2. That's 2 into 10 raised to the power negative positive 5 volts per amp is ohm, and that's basically 200 kilo ohm, right? So that's a 2 and 5 zeros. That's 200 kilo. So that means that this resistor is supposed, R1 is supposed to be 200 kilo, right? Now, it's of course important to analyze this circuit. Now we did all of these things. Now it's important to analyze this circuit and see basically how it really behaves. So let's see. Okay, so now let's analyze this circuit. Let's see what happens if you actually put together this circuit, and if you turn the switch on and off, meaning that if you put it on position A and or position B. So what happens if basically if you put the switch to position A, so essentially oh, and one thing that I forgot is that basically the value of R2, this you can just simply arbitrarily basically choose a resistor that is some value, for example, between, I think if I remember correctly, these are some basically tricks of the trade, meaning that these are the kinds of things that you just simply take from basically years of experience, and it's usually based on what works, what doesn't work, meaning that of course what we are doing here is mainly theory, but in theory, theory is always useful if it's based on experience as well and based on what works really. So for example, the value of this resistor that you put here is usually one of the tricks of the trade, and what they do is that they just arbitrarily choose some value of resistor, which is somewhere, I suppose, between 10-20 kilo ohm all the way up to 1 mega ohm. You can choose any resistor value that basically that you have in your junk box. And so since basically we chose this resistor value 200 kilo ohm for R1, we can choose the same value resistor over here, and there is no problem there because it's less than 1 mega ohm, and there is no problem there, right? So that's basically about that. Now let's see what happens if you put the switch on position A. So then what happens is that the supply voltage comes over here through this resistor R1, and it goes through to the base of this transistor, and this transistor goes to, basically from the emitter goes to ground, and then your transistor essentially turns on because of the fact that basically we actually designed the circuit in such a way that the transistor would actually turn on. So since the transistor turns on, so over here then you would have a current of basically 5 milliamps based on basically that you would have a current of 5 times 10 raised to power negative 5 amps basically over here that goes to ground basically, and then there would be a current of basically I2, which is this 5 milliamp that goes to ground. And since this transistor is turned on, there is no voltage over here, right? The voltage drop over here is actually zero with respect to ground, because there is no voltage drop across the collector emitter junction of this transistor. And as a result, there is no current flow through to the base of this transistor over here, and this transistor is turned off, right? So which means that basically when the switch is set to position A, your Q2 is turned off, which is basically what we found that basically previously as well. Now when you set this position, when you set this switch to position B, the base of this transistor is through a 200 kilo ohm resistor is tied to ground, right? That is tied to ground, and so that means that there is no base current for this transistor. If there is no base current, that means that there is no collector current for this transistor, and this transistor is essentially turned off. Since there is no collector current, that means that the whole current from here, the whole supply voltage, goes to this point through this resistor, and then goes to the base of Q2, and it turns Q2 basically on. So Q2 is basically turned on, and so what happens is that, and then there would be a current of basically I2, which is 5 milliamp through the base of this transistor, which causes a current of basically 100 milliamp through the collector of the transistor, I of C2, or basically 100 milliamp. And that basically means that your transistor is actually turned on. So that's basically how the circuit works. Now let me take a look at the values of this exercise and see if we have found everything correctly. And question number 4. So basically the right answers over here are basically R3 is supposed to be 2 kilo ohm, which is correct, and R1 is supposed to be 200 kilo ohm, which is correct, and R2 is supposed to be 200 kilo ohm, which is an arbitrary value, which is correct. And that's basically the value of the resistors that you would use. And again, in case you don't, you're interested in a good text on electronics, a basic beginner text on electronics that teaches you essentially all the important things, you can essentially go with the same text that I'm working on. And surprisingly enough, this is actually a very good text. It's called, basically the text is called Complete Electronics. Complete Electronics by Self-Teaching Guide. Self-Teaching Guide with projects. and it is from Earl Boyson and Harry Kybet, if I'm pronouncing that correctly. And it is from the ISBN of this book is ISBN is 978. Let me enter the ISBN into, for example, Amazon.com. Let's see if we can get the book over there. If you go to Amazon.com, I think you would get this book mainly second-hand because the book is pretty old. 978, 118, 21732, 0. And that's the exact book over here. It costs actually absolutely almost nothing. It's the paperback, $13. You can see $13 to $21. That is the book that I'm actually using. Of course, I do use a whole range of things, but essentially you need to have a text in order to understand the basic concepts of electronics. And the problem with most electronics books that you would find on the market is that they talk about things that don't matter. For example, they talk about, cells and batteries and types of lamps and types of, for example, I don't know, types of, for example, solders, types of, I don't know, those kinds of things. You can, whenever you need them, you can easily find them on the internet, on YouTube. You can find some reviews and things on the internet, and you can find that. But the essential important things about electricity and electronics you can find in this book. It's actually a great book. Okay, I hope that you enjoyed this video, and I'll see you in the next video, and thank you.